Hello, folks. This is the activity in Lab 3 for the course FEA with Catia V5. Uh, it is activity 1, and what we have here is a block like that, and the dimensions are given up there. And this is being pulled on both sides with a force of 2,000 pounds. Now, this problem has three planes of symmetry. So in this activity, I will try at least to do two of them. One of them is to take one of them, the first one is to take all three planes of symmetry and solve the problem. And then I come back and do it with no planes of symmetry taken at all. Okay. Now we are given here a force of 2,000 pound on that face, and of course the same thing on the other face back there. But applying a force on a solid model, you have to be very careful because right underneath the applied force, uh, think about it like that. The stresses become maybe unrealistic, and therefore you have to stay away from it. So I'll do this problem twice, one with actually a force applied, and then repeat it with pressure applied. Okay. All right. Let's move on. It is a single part, and therefore I will go ahead to Katia and start with a part file. Although things can be done in assembly if you want, but I don't want to confuse you. So I'm going to make the whole object and then cut it three ways. Okay, so on this vertical plane, I will sketch. Now the dimensions given are in inches. So I'm going to draw a centered, on purpose, a centered uh, uh, rectangle, because later on, once I pad this thing, I'm going to cut it with these symmetry planes. So let's use the dimension of this 2, 4, 10. So this is going to be 10 inches. My units are already in inches, so that's good. 10 inches, because in inches I don't have to write inch. And this is 4, 4. And then in the middle, there is a circle. Actually, there's a hole, but the way we do it, we're drawing a circle, which is going to turn into a hole later on when we pad. And this is the radius of that circle, I believe, is 1 inch. So the diameter is 2 inches. Okay, exit, and pad it in both direction, mirror extend. And the reason I do mirror extend is because I want to cut it later on with the appropriate planes, for example, YZ plane or XZ plane, whatever it is. So 1 inch in each direction, and we say, okay, there we are. Let me save this thing. File, save management, save as. Let me go to lab 3, lab 3, so one folder up. So do not delete. Lab 3, activity 1. I'll call it part. It doesn't matter, but I can call it, for example, a part of problem 1. Remember, these names are important because you don't want to overwrite them later on when you write the midterm and the final. Okay, so this will make me realize that this is a part of problem 1. How about that? Oops. Problem 1. Okay, good. Now, let me apply material to this thing. You have to. If you're going to do finite element, you better tell me what material it is. So metal, let's, for example, apply some dummy material. These things, I think it says aluminum. So aluminum right here. Yeah. And put it on the part. We say okay. However, these are the default. If you double click on the aluminum, in this tree. Oops, did I crash? Ooh, I think it crashed. Let me see one more time. I'm afraid that I might have a bug in the current version of Catia that I have, that I may not be able to apply material, but apply material or change it. I'm sure you can. This is the one that I wanted. Let me double click on this. Oops, apply material. Let's try it. Apply material. If it crashes, it means that I have a bug. Now you won't have that problem. When I did the installation here, or when the installation was done, apparently there was an issue. So let's see now. Metal, aluminum on that part, and I say okay. Now aluminum is applied, but if I want to change the properties as the problem description says, I have to double click on this and go and change it. Unfortunately, I have a feeling that if I double click on this thing, it crashes. Yeah, so that's my installation issue. So don't worry about it. Just I will use the default properties, and you guys go ahead and double click on the branch which says aluminum, and put the appropriate numbers in there. Now, uh, in all like, I mean, unless I ask you to put specific numbers in there, you can use the default properties in the database. So I'm sorry about this, but that has to, I'm going to check into it to see what the issue is. So there are default material properties that are being used here. Now, you save everything. Because I already put it in that folder, I don't have to do anything special. So now we're going to go to analysis and simulation, generative structure analysis. What Catia does is that it tells you that we are doing this with by default static analysis with element that size. This element is probably terrible as far as the size goes, but let me say okay. If you want, you can look at the mesh. You can look at the mesh visualization, and change the rendering here. Okay, that's fine. Now this is a big mesh, so I don't want that. I talked about these things in class. I'm just doing a quick review of what I did in class here for you to if necessary to uh, look at it later. But we talked about mesh issue of mesh refinement and things like that in class. So let me use instead of size zero point 0.6, I'll use 0.3, and I'm going to use linear or parabolic. I'll use parabolic. How about that? Say okay, and right click mesh visualization. Parabolic elements are more accurate, but they're more uh, resource intensive. So to do the rest of the problem, I have to deactivate this mesh. Okay. And by the way, if you don't want this shiny little thing to show up here, change the material rendering to shading with edges, etc. If you put it on material, you see that it comes up with the illusion that you have put the material on it. Now, this is fine. So immediately you go to File, Save Management. This analysis we did not save, so I'm going to save as. In that same folder, this is Lab 3, Activity 1. I'll call it for Problem 1. How about that? For Problem 1. And then say OK. All right, so what we're going to do is one thing I realized is that first I told you that I will use three planes of symmetry, and I completely forgot about that. So let me go back to my parts. Let me go back to my part, and I expanded the tree and double click on this line. See, you can stay in analysis, expand the tree, double click on the part, and okay. We are in part design. So what I wanted to do is to want to cut this thing three ways. So look for the saw in the, let me see now, the saw is in probably transformation. Let's find out. Oh, there we are. Remove this thing. See, there is a saw here. You click on it. It says select the plane that you want to cut your object. So this plane, and arrow means which side you want to keep. It doesn't matter for me. So again, one more time. This time the other plane, the other middle plane, and it doesn't matter order, which side you pick doesn't matter. And one more time, and like that. So basically, I'm using all three planes of symmetry. I would have done it before going into analysis, but I forgot about it. So I went back and cut it. Now I go back to analysis. You see that the part that is in your analysis is actually, if you say, show me the mesh, right click mesh visualization, it actually will take the quarter and mesh it. Okay, so I saved some time by not scrapping the analysis file. I went back to the part design, make the appropriate cuts. So deactivate this, put the put put the cursor there, right click deactivate, and proceed. Now these three planes that I cut it, they are planes of symmetry, and what that means is that you can think about it as being on roller. So plane of symmetry and roller, Catia does not call it roller, but there are these icons that it has. One of them, which is called slider surface, is actually a roller. Behaves like a roller. You click on it, and you select this, and you select that, and you select this side. These three planes are planes of symmetry. Okay, and when you think about it, there is, because of the symmetry, there is no resistance perpendicular to it. It just stretches or it shrinks, etc. Now we're going to apply a force at this end. So apply a force. The force is on in the loads toolbar. Those toolbars, if it says force, let's say apply force first of all on this face, magnitude in the direction y. Now it was a total of 2000 on this face, but I'm taking 1/4 of the face, so that's going to be 500 Newton, and the direction seems to be right. Now I don't put anything here because this is on a roller. The piece that has a force on it is way on this side, on the left side that we got rid of it. Okay, so do not put force here and force there. You can put it, but it's just going to be wrong. Simple as that. Okay, good. And this is it. Save everything and run it. Here's the calculator. It's called compute actually. Assuming that there are no mistakes, this ignore this message. First of all, it's a warning, and it's not going to have any effect. The newer version may not even give you that message. So let's go ahead and say yes, run it. There we are, finished. So first look at the deformation. The deformation is here, okay? So let's animate this thing. Animate is this strip of film. Okay, we can slow it down. So here, let me slow it down. But one thing you can see that there are some unrealistic stuff happening at these corners. That's because I'm applying a force. If I apply pressure, and I will do that in just a minute, you'll see that you don't get this bulging out of these corners. So we say, okay, let's look at the deflection. Deflections, you can see that every point moves, every node moves, and the only thing is that these move a lot, and that's because of the fact that I'm applying a node. Now this is a very small value, so first of all, small inches, of course it makes sense because this is a piece of aluminum, thick piece of aluminum. You put, I don't know, 2,000 pounds on it, it doesn't get much displacement. If you look at the average ISO, I double click on the contour on those arrows and average ISO, and I want material shading. Material shading, notice that it does give you the colors, but not very good. I mean, it's in the form of line drawing. So if you go to material shading, there we are. Incidentally, if you want to see your element showing up, you have to go and activate that. So you go to this rendering, the very last one, you click on it, and notice that automatically these things be shown. There are other things you can do here. All right, good. Now let's look at the stress, von Mises stress. So von Mises stress, you can see that, well, first of all, the units here. Look at the units. This is in Pascal. If I'm using inches and things like that, let me go change my stress unit. So we go to tools, options, scroll down until you get stress or pressure. Pressure, let's change it to PSI. Where is the PSI? Right there. Now, that might do the job, but I'm pretty sure that in the newer versions of Catia, you also have a stress here. If you can't get it, just click on the magnitude. It puts it in alphabetical order. Let's see. Does it have a stress? You see, I don't see it here. I think in newer versions they did add stress, but this pressure will take care of what I want to show you. Yeah, it doesn't show you that. On your version uh, that's installed at the university, go and select the stress. If pressure should work, but if it doesn't work, go and choose the stress to PSI. But anyway, right here, PSI. 501 PSI is nothing. And those are actually very big at these corners. You can see that, okay? So, wait a minute. I think my force was wrong. Let me go check here. I don't think I put the correct force here. This is nothing. So let me go and check my load. Newton. Oh my God. That was pounds. So I have to change this thing to lbf. Okay. Yeah, that's almost 4 times, 5 times bigger. Run it again. That 2,000 pound in the description of the problem was in pounds. I did not pay attention to the fact that in the dialog box it was units. So there we are. Okay, don't let it bother you. Look. There is this. If you look in this toolbar where you have the clip of film, there is this amplification magnitude. Click on it and say default. There we are. That's a lot better. But it shows you about 2,000 psi, which is still nothing. Now, uh, by the way, if I look at only the stresses here, I won't see these sharp corners. And let me deactivate this plot, and make a group in here, a group of elements in here. The group is done many different ways. One of them is, for example, let's make a box group. This is a gigantic box that it made. So let me resize it by clicking on this box. You can resize it so that it basically gets to where you want to go. There we are. I wanted to stay away from those ends where the unrealistic stresses are. You can do sphere group and other things, so just keep it like this. You can hide it. If you activate the one meso stress or double click on it, and on the selection tab, say, show me just the stuff in the box. There we are. You see, the stuff in the box, the biggest stress is supposed to be appearing here, and it's roughly 1,000 psi. Okay, all those unrealistic stresses are gone. Those were way down here. You see that they were way down here. But if you want to get it back now, just say, show me everything. Right there. Good. So let me deactivate this block first of all. Go and delete that force. Go and delete that force. Delete it. Change it into pressure. The pressure is what the load toolbar is. This is the force, this is the pressure. You select that face and make sure you put the right value. Now the pressure, if you look at 2,000 pound, it is applied on that entire end face. That entire end face has an area of it was 2 by 4, 8 pounds, 8 square inches, 8 square inches on this entire face. We're taking 8 square inches, we are applying 2,000 pounds to it. So 2,000 divided by 4, 2,000 divided by 4, because this is 1/4 of that surface, that's going to be 500 psi. So over here, I'm going to say 500 psi. But if I say 500 psi, it compresses it. If you want a tensile, you put a minus, because by default pressure is always compressing the object. You see that? If I had put a positive, it would have compressed it. Say okay and run it. Done. And if you look at the stress here, you can deactivate this or activate it again. You see, we don't get all those unusual stuff down here. And in fact, if you look at the pressure or stress is right here, and we have yeah, your what is this? Yeah, the biggest stress is here as we expected. Now, one thing that's I notice is that if the hole is small, the stress concentration factor, I believe is it 3 for a small hole? That stress concentration factor should be 3, if I'm not mistaken. But anyway, this is not a small hole, so that's why you don't get 3. If you apply a 2000 psi, sorry, it's almost 3 actually. We applied 500, is a 500 psi. If you multiply it by 3, you get 1500. But this is not a small hole, so it's a little bit bigger. Now, let me save this thing, because what I want to do is I want to go and go back to my part and remove those splits, so I can deactivate it or delete it. Let me deactivate it and deactivate it. The other one deactivate, and the last one deactivate. So basically, instead of redoing the problem, I have got rid of or deactivated the cuts. So we go back to the analysis. Okay. Now, if I run this thing, well, first of all, I put the pressure on this side, but I also have to put it on the other side. So let me double click on the pressure on this side. It's already selected. Now I'm going to put it on the other side so that you have 500 on both sides, 500 psi on both sides. If I run this thing, it will bomb out, and I'll show you why. So let me go run it. Yeah, there are some surface sliders that we should delete actually, because those uh, those surface sliders were not those surfaces are not there. So delete this. You have to delete it. Can I deactivate? No, you have to delete it. Good. Because remember, those surface sliders we put there because they're planes of symmetry. We don't no longer have it. So we're going to run it. It will bomb out, but for a different reason. You can see that it says that matrix singularity is found, etc. You can see this. So it means that there is an issue, because notice that if this object was sitting in the back of a truck and the truck was moving and I pulled on both sides with 500 psi, you cannot tell me where the block is because the truck is moving. In fact, if you say, okay, uh, let me activate the translation, or the first one, deform shape, activate deform shape, and again, fit it, default, good. If you say, show me the what is happening, you can see that it's moving as a rigid body. When I had those planes cut mates, because of the surface slider or roller, it could not have moved. Now I've got to fix this, and I insist on doing it. So deactivate this. Okay. So what I'm going to do is I'm going to remove that rigid body motion. So I'm going to click on this icon here. See, this was a surface slider. This is a clamp. We're going to use that. So I'm going to, for example, just click on this very last icon. It says, okay, what do you want to do? First of all, I uncheck all of these. These last 3 rotations has nothing to do with solid elements. I can leave it or I can take it out, but it has no bearing on solid element formulation. Therefore, I just took it out. You can leave it on. The rotation, you can leave it on for solid element. It's not going to have any effect. Now, I take a corner point and I say, hey, don't go in any direction. Okay, so we say okay. Now that corner point, although it doesn't move, this will still be free to rotate. So I'll take another pinch about that point. So I'm going to do another one. I'm going to say, okay, this corner point, I don't want you to move in the direction Z or X, but it's okay, Y, but it's okay to go in the direction X because it actually can shrink. You see, this, as you pull the sample, it actually should be able to shrink. Therefore, I should not say that this point cannot move in direction X because this point is not moving in direct. If that is the case, this cannot be shrinking. And finally, if you think about this thing, this whole thing can now rotate about the x-axis. So I'm going to take one more point, for example, this corner point, and say, do not move in the direction Z. This prevents the rigid body motion. This is called the 1-2-3 rule, removing the rigid body motion. And I can tell you that in all of the problems that I'm going to be giving you in the midterm and later on in the final exam, you will have to use, first of all, as many planes of symmetry. You will have to use as many planes of symmetry. Uh, And if there are none, of course, if there are none, then you have to watch out with the rigid body motion, and therefore should be able to handle problems like this. Right now, this is the very first problem that we are doing. It really doesn't matter, and I expected you to use all planes of symmetry. This is getting more complicated, as you see. You might say, I didn't have to think about planes of symmetry. Yes, but if you don't, then you can see you have to pay a price. You do more work. Hopefully, I didn't forget anything. Let me first of all save everything and run it. This time, the 1-2-3 rule will remove the rigid body rotation, rigid body motion, no error messages, and it will run done, as you can see. Now, if I activate the deform shape, you see that it's stretched in both directions. Now, if you can't see it here, that's because we already made sure that when it bumped out, we already made sure that the scale was set to default. Let me go back to this and say default. See that? It made it a lot smaller because I wanted to see what went wrong. But now, default, there we are. And you can see that as you stretch on both sides, the sample does what it's supposed to. So in this problem, I used three planes of symmetry. It was fairly straightforward. You just had to realize that the force, when you calculated the pressure out of it, had to be, you know, properly taken into account. In other words, the force divided by that total area will give you pressure. That's what I applied. Remember, this is the first time you're doing FEA in Catia. So you have 10 more weeks or 8 more weeks to get used to stuff. Okay, so that's it. And good luck.